So actually, you should tell me if I'm like over time because I planned for 25.
Oh, okay, yeah. So 25 including questions. Okay.
I said it was 25 plus 5. So
sorry. Okay.
I'm gonna try to yeah, to go a bit faster or just like stop me at some point. Okay. So thank you very much for the invitation. And I want to say that all the work I will present was done in collaboration with Brent Vaughan. So currently, it's possible to record from multiple brain areas simultaneously and from many tens of neurons in each area. And so we can start to ask the question, how does activity propagate between brain areas? And this is a long-standing question in the field of theoretical neuroscience. So initially, it had been addressed using fully feed-forward networks with random connections between layers. And in those types of network, it has been observed that either the spiking activity fully synchronizes as it propagates down the layer, or it disappears. And this is at odds with experimental recordings of the ventral visual pathways that have shown that activity in different areas stays pretty much irregular. So then it has been observed that if we introduced recurrent excitatory and inhibitory connections in our network, we can generate an asynchronous state. So basically, this is due to the fact that the excitatory input is balanced by an inhibitory input into each neuron onto the network. And that's why we can get this irregular asynchronous spiking activity. And this yields a distribution of spike count correlation, which is rather broad, as is observed experimentally. However, the mean goes as 1 over n, and the variance as 1 over square root of n. And this is at odds with experimental results that have shown that indeed the distribution of the spike count correlation is rather broad, and its mean is close to 0. However, it's positive and significantly different from 0. So then some specially organized network have been introduced, among others by Robert Rosenbaum, who is gonna talk just after me. And basically when we are in this specially organized network, we can set our network in a parameter regime where the recurrent projections are broader than the feed-forward connections. And when that's the case, we cannot be in an asynchronous regime. So basically, we need the opposite to be in the asynchronous regime. We need the feed-forward connections to be broader than recurrent connections. But when we have both recurrent connections, we are in this interesting regime where we can move from a stable, irregular-looking spiking activity with a mean spike count correlation, which is close to 0, but slightly positive, towards a pattern-forming regime where we really see complex spatial-temporal dynamics, and this yields even broader spike count correlation distribution with a higher mean. And so in my work, I will only work I will work with a 3-layer network with spatially organized connections, and I will always be in a non-asynchronous regime. So I will always have the feed-forward connections which are narrower than the recurrent connections, and so I'm never technically in the asynchronous regime, but I can move between the stable and the pattern-forming regime. So in the input layer, I have homogeneous Poisson processes, which are homogeneous in space and in time. And each layer is feed-forwardly connected to the next through these feed-forward connections, which have a broadness of sigma feed-forward. And then the sender and the receiver layer consist of excitatory and inhibitory neurons, which are recurrently connected with broadness sigma E and sigma I. And these neurons are organized on a 2D grid with periodic boundary conditions. And so using this network as a modeling tool, we can ask the question, how does communication between sender and receiver is affected by emergence of complex dynamics, either in the sender or the receiver. So first of all, we can look at what happens when we destabilize the EI balance in the receiver, in this case, especially by increasing the broadness of the recurrent inhibitory connections. And we see that even if our sender area is set in the intrinsically stable regime, then we can have emergence of complex spatiotemporal patterns of activity in the receiver. Now we can do the opposite. So now we destabilize the EI balance in the sender area, and we keep the receiver area in the intrinsically stable regime. So we have emergence of complex spatiotemporal patterns in the sender. And because we have these feed-forward connections, which are also spatially organized, basically we see that these patterns are propagated to the receiver layer. So then we were interested to find some kind of global measure of the neural dynamic of the within area neural dynamics. So what we were interested in was to assess within area shared dimensionality, and to do that, basically we imprinted a disk with a given radius onto our grid of cells, and out of this disk, we would pick randomly 50 neurons, which are responsive enough to the task. And then, so the reason why 50 neurons is because it's in the order of magnitude of the number of neurons which can be experimentally recorded in a brain area. And then we would compute the full covariance matrix C. And through factor analysis, we can separate it into a shared component, C shared, and a private component, C private. So C private is simply a diagonal matrix with individual neuronal variances. And in this work, we are interested by the shared covariance matrix. So we can apply singular value decomposition. And then basically we obtain the shared eigenvectors in the columns of U, and the shared eigenvalues in this diagonal matrix lambda. And participation ratio, which is the measure we are using to estimate within area shared dimensionality, is defined as the first moment of the shared eigenvalue squared divided by the second moment. And visually, what it means is that if one eigenvalue is much stronger than the other eigenvalue, this indicates that the activity looks like an elongated blob in this high dimensional neural space. And so this would yield a low participation ratio or low dimensionality. On the other hand, if the lambda I are very similar to each other, this is reflected by a big like hypersphere of activity in this high dimensional neural space. And this would yield a high dimensionality or high participation ratio. So first of all, we can investigate the case where the sender is in the intrinsically stable regime. And what we observe is that as we increase the disk radius from which we sample the 50 neurons, the estimated shared participation ratio increases. But even when we pick neurons from the full grid, we observe that the shared participation ratio is much below the theoretical upper bound of 50. So this really shows basically that the shared participation ratio value in itself doesn't really have a meaning. But what we are interested in is more how it is modulated by different neuronal dynamics. So now if we look at the receiver area, and as we destabilize the EI balance by increasing the recurrent inhibitory connection sigma I, we observe that this has the effect to decrease the estimated dimensionality in the receiver. So what is interesting now is that we can do the same type of analysis in the scenario where patterns emerge in the sender and they are inherited in the receiver. And we observe that the shared participation ratio, which is estimated in the receiver, looks very similar in both cases. So by only analyzing the receiver activity, there's no way to tell if the shared variability emerges from recurrent connection, as it is the case here, or if it is inherited from the sender, as it is the case here. Okay, so now it's really nice because we have this modeling framework, and we have this simple parameter that we can modify to destabilize the EI balance a little bit more, a little bit less. But if we record from a brain area, we cannot know a priori what are the parameters of the network we are studying. So we needed some sort of order parameter for the degree of pattern formation. And a natural way to address this question is to compute spatiotemporal Fourier transform and to get the power for each combination of temporal frequency omega and spatial wave number k. And you can see that for different broadness of the recurrent inhibitory connections, we have a different spatiotemporal signature of the neuronal dynamics. And I should note that the scale is different for each plot. So the maximum is increasing as we have more and more EI destabilization. So it seems that the peak of power seems to be a good order parameter for degree of pattern formation. And interestingly, the signature of this spatiotemporal dynamics is very different for different sigma I. So now I'm going to use this peak of power as order parameters for the degree of pattern formation. And I'm interested to understand how does pattern formation affect the communication between brain areas, so between sender and receiver in this case. So to address this question, I used a method which has been developed by Semedo and colleague. And so basically, the aim is to try to predict the activity in V2 using the activity in V1. And they have shown that using a few predictive dimensions, which are like a subspace of the V1 activity, they could predict very well the activity in V2, and that instead they would need much more dominant dimension in V1 to predict V2. So this is basically a reduced rank regression measure between the sender activity S and the receiver activity R. And so this reduced rank regression matrix is constrained to have a low rank, which is M. And then this regression matrix is a low rank approximation of the ordinary least square solution. And then to assess predictive performance of the communication subspace, we take the average normalized square error over 20 cross-validation folds. Okay, so basically we can look at our first network where we have emergence of patterns in the receiver. And we see that on the x-axis, we have our order parameter for the degree of pattern formation. So as we have more and more pattern formation in the receiver, the prediction performance of the communication subspace decreases. However, now if we look at our second type of network, where we have emergence of patterns in the sender, and these patterns are inherited in the receiver, we see that as we have more and more, as the peak of power in the receiver increases, the prediction performance increases. So we have like different effects on the communication between the two brain areas, depending on the scenario in which we are. So actually, it seems that the matching of dimensionality in the sender and receiver is a better predictor of communication quality. So now on the x-axis, instead of looking at these other parameters of neuronal dynamics, I plot the difference between the shared participation ratio in the sender and the receiver, and we observe that if there's a mismatch in dimensionality, the prediction performance of the communication subspace is pretty low. On the other hand, if there's a good match in dimensionality between the sender and the receiver, the prediction performance of the communication subspace is high. So this we can conceptually depict in this way. So here our sender is in the stable regime. So it looks like very high dimensional manifold in this high dimensional neural space. But as we have more and more pattern formation in the receiver, we saw that it has the effect to decrease the shared participation ratio in the receiver. And so there's a mismatch in dimensionality, and that's why we have poor communication. On the other hand, when we have emergence of spatial temporal patterns in the sender, we already have like a low dimensional manifold in this high dimensional neural space in the sender, and this low dimensionality is propagated to the receiver, and that's why we have a good match in dimensionality, and this yields faithful communication. But now the interesting question is the matching of dimensionality really the only important criteria? And until now, I always destabilize the network using I destabilize the network spatially by increasing sigma I. But we know that we can destabilize this network in different ways. So another way to destabilize the network is actually just to increase the time constant of the inhibitory neurons, because this also doesn't let the inhibitory neurons track the excitatory neurons so faithfully, and that's why we have a destabilization of the EI balance. And so now we ask the question, what happens when both so I start with a network where the sender is destabilized temporally, and then the receiver is destabilized spatially. So in this network, we have different patterns that emerge in the sender and the receiver. And we are going to compare this network to a network where there's only emergence of temporal patterns in the sender, and the receiver is intrinsically in the stable regime. So that's a network where patterns emerge in the sender only. So as expected by design, the match of dimensionality in both network is pretty good. So if we look at the difference in the shared participation ratio in sender and receiver, it's close to 0 in both cases. So since we have a good match in dimensionality in both cases, we would expect a priori that we have good communication between sender and receiver in both cases. However, it's not the case. Basically, when we have new patterns that emerge in the receiver, we observe that it has the effect to strongly decrease the prediction performance of the communication subspace. So my intuition there was that the alignment of the manifolds between sender and receiver was not as good when different patterns emerge in both areas. So to investigate if it's the case, I used a method based on canonical correlation analysis, which has recently been used by Gallego and colleague. So basically, the idea is that they were recording from the same brain area on different days. So they had like different neurons on each day, and they would just project the activity on each day in a low-dimensional manifold, and then try to realign these two the projected latent dynamics on different days, and basically if the canonical correlations are high, it means that it's possible to well align this projection on the low-dimensional manifolds. And if canonical correlations are low, it means that they cannot be well aligned. So in my case, what I'm trying to do is I'm trying to align the latent dynamics in the sender and the receiver.
5 minutes till next speaker, Olivia.
Okay.
Okay.
Thanks. Okay, so basically what we see is that if we look at the difference in canonical correlation in the case where patterns emerge in the sender only and where patterns emerge in the sender and the receiver, we see a positive difference. So it means that in the first case where patterns emerge in the sender only, it's possible to align well the latent dynamics in the sender and receiver. And in the second case where new patterns emerge in the receiver, we have a misalignment of the manifolds. So basically, we also need a good alignment we don't only need a good match of dimensionality between sender and receiver, but we also need a good alignment of the manifolds between sender and receiver. Okay, so this is a summary of what I have said so far. So we need a good match of dimensionality and a good alignment of the latent dynamics to have faithful communication. Now, it's a little bit surprising because we know that our network has strong feed-forward connections between layers. So it's kind of surprising that the communication between sender and receiver seems to be poor. So here we were looking in particular at a case with low prediction performance of the communication subspace. So it's a case where we have a mismatch of dimensionality, we have emergence of patterns in the receiver, and we freezed the spiking activity in the sender and use different initial conditions for the membrane potential in the receiver. And we see that macroscopically, the activity looks very similar for both trials. And actually, a weak perturbation only yields macroscopic chaos. So to conclude, a mismatch in dimensionality or in alignment of shared variability in sender and receiver disrupts communication. However, the receiver is always effectively driven by the sender in our network. So it shows that linear measures have limited applicability when elucidating the flow of information in neuronal system with complex dynamics. And with that, I want to thank the funding sources and of course, Brent. And if you're interested, this work is as a preprint on the Boari archive. And I'm very happy to take any questions.
Thanks so much. Do we have time for a quick question? I had a quick question. So I didn't fully explain what are the mechanisms behind the shared variability exactly? Are you able to sort of elucidate a bit more about that?
Okay, so let me know if I'm not answering the question. So basically, in the purely balanced network, we are in the asynchronous state. So all the neurons are kind of the activity is kind of independent to each other. Now, if we destabilize this EI balance, we will have like neurons that are close to each other, which will be more correlated. The pairs will be more correlated than neurons that are far from each other, because we have this spatially organized connectivity. So basically, that's why we have like these blobs of activity that we see in the spike clusters. So that's what we call shared variability.
Okay, thanks again, Olivia.